Hey everybody, welcome to the last lesson of this week. So we only have two lessons, two short lessons this week because you guys are writing your test. So here we go. This lesson is on the common ion effect. Now I know we touched upon the common ion effect when we looked at Le Chatelier's principle. That was a qualitative method of having a common ion, but now we're moving to a quantitative method, which is the calculations that we're going to be looking at with respect to the common ion. So take, for example, this equilibrium here. So you have lead chromate, so lead, I should say lead 2 chromate. When it dissolves, it produces lead ions, lead 2 plus ions in solution, and some chromate ions. Everything's in a 1 to 1 ratio. It says if we add into the solution, or add lead 2 chromate to a solution of sodium chromate, as an example, then the equilibrium should move left. So think about that. If I were to take some some sodium chromate, and I were to dump it into a solution that already contains lead chromate, well, what's happening is the sodium ion is just kind of floating around in solution. It's not doing anything, but you'll notice that there's a common ion between the two of them. They both contain chromate ions. And so if I add chromate ions into solution, it's as if I'm adding a product. And so if I add a product to a system that's at equilibrium, it will push the equilibrium to the left and cause precipitation to happen, cause that system to move left, produce more of this solid lead chromate um, product here. Now, if you're confused about why that happens, go back to the lesson on Le Chatelier's principle. In any case, even if this is happening, even if we've added some some sodium chromate to a lead chromate solution or vice versa, the KSP does not change because the KSP is constant. And so if the KSP is constant, and I know that I've increased the concentration of this, in order to keep this value constant, I must decrease the concentration of this. So the only way to decrease the concentration of this is to turn this aqueous lead into lead chromate solid. And of course, when you do that, the solubility goes down. I can't dissolve as much. So that's kind of the explanation as to why this system happens. So let's look at a problem here. So it says here the solubility of pure lead 2 chromate in water is 4.3 times 10 to the minus 7 molar. So I've given you the KSP value here. Pardon me, I've given you the X value. So it says qualitatively predict how the solubility will change when it is placed in a 0.1 molar solution of sodium chromate. Well, if I'm going to qualitatively predict this, I need to figure out which direction it's going to push. I know that if I'm putting it into a solution that contains that particular ion already in it, then it should make it less soluble. So if it makes it less soluble, it means it's going to push the equilibrium left. It's going to lower the solubility. So let's see what happens. It says, what is the new solubility if the KSP of this particular solution is 2.3 times 10 to the minus 13? So let's try this out here. So this is a little bit different than what you guys did before. So usually you have zeros here, but in this particular case, you are starting out with chromate ions already in solution. So instead of a 0 and 0, it's 0 and 0.1 for the chromate ion here. All right. We know that as this lead chromate tries to dissolve, it's going to dissolve in a 1 to 1 ratio. So we have a plus X here and a plus X here. And so we produce an X and a 0.1 plus X value here. Now, there is a way to make this a little bit easier on our math instead of having to solve for a quadratic. So in some of the problems that you would have had to solve for, if you end up with an x squared, as you would in this particular question here, then what happens is you have to solve using a quadratic. But there is a shortcut, and I'll show you what the shortcut is in just a second. So I set up my expression, KSP is equal to 2.3 times 10 to the minus 13, which is equal to the product of both ions raised to their coefficients, but of course the coefficients in this case are 1. So it's just equilibrium x and 0.1 plus x. So it's x times 0.1 plus x. Now I've written here ignore x. Now why do we ignore x? If this x was significant, we could not ignore it. But because the solubility, the KSP value, is so tiny, then we can ignore that x because we know that 0.1 plus this value is still going to be 0.1. And I'm going to show you guys what I mean by that, or how to do that, the negligibility, and see whether x is actually negligible. So in order to do that, you take whatever's in the bracket, so in this case it's 0.1, with the x, take that value, 0.1, and divide it by the KSP, or any k value for that matter. So you can actually zoom forward and go back a little bit to your other problems and solve them much faster than using the quadratic formula if you use this simple check. So it's 0.1, or whatever's in the bracket with the x, divided by the k value. Now in this case it's a KSP, so we're going to divide it by the KSP. So 0.1 over the KSP is equal to 2.3 times 10 to the minus 12. Or pardon me, 10 to the power of 12. This number is absolutely massive. Now we check it against 500. Now I have seen textbooks that check it against 100. I've seen textbooks that check it against 300. The larger the number you check this, the more accurate your answer will be. This is basically saying to you that this x value here is at least 500 times smaller than the 0.1. Now obviously in this particular case it's a lot smaller, but this value here, whatever number you use, it's going to tell you it's at least that much smaller. So because this number is enormous in comparison to 500, this number for x is going to be really tiny. So we can just ignore x and just assume it's 0.1 in the brackets. So x times 0.1 becomes 0.1x. I take that 0.1, divide the KSP on the other side, and I produce an x value of 2.3 times 10 to the minus 12. Now, 2.3 times 10 to the minus 12 is a very, very, very tiny number. But it's not so much that it's tiny, it's how much smaller it is than the number that was produced or given in the question for the solubility, which agrees with our prediction. We said that the solubility is going to be much, much, much lower. So 2.3 times 10 to the minus 12 moles per liter is much, much, much smaller than 4.3 times 10 to the minus 7. And in fact, it's on order of 5 times the magnitude. So we're talking over 10,000 times smaller. Okay, so this agrees with our prediction. It agrees with our prediction in that the value that we got as a result of this 0.1 here is much, much, much smaller. And so it agrees with our prediction that we made. Is everybody okay with that? I hope everybody's good. So let's go on to another type of problem here, and this is predicting whether precipitation happens. So sometimes you mix chemicals together, and you want to know whether the concentrations that you have in the solution are large enough to produce precipitates. So it's to determine if a precipitate is going to form, you have to compare the KSP value to the ion product quotient, which we will call Q or QSP, sometimes written. So if this is just like before when we looked at the reaction quotient, when we looked at our QC values versus our KC values, now we're looking at QSP versus KSP. So of course we know if Q is equal to K, then we have a saturated solution and it's reached that saturation point. If we have a Q value that is greater than KSP, it means that a precipitate will form. Basically what that means is the amount of ions you have in solution is greater than what the solution can hold in terms of the amount that it can actually dissolve, and so it will push backwards and produce a precipitate. If you have less than, then you don't have a precipitate forming. You need to add more solutes in order to get a precipitate to actually form. So here's a sample problem. So it says here, will a precipitate form if 100 mils of a 1 times 10 to the minus 3 molar lead nitrate solution is added to 100 mils of a 2 times 10 to the minus 3 molar solution of magnesium sulfate? And it gives us the KSP of lead sulfate. So when you look at the expression, so we've got lead nitrate mixing with some magnesium sulfate to produce some lead sulfate and some magnesium nitrate. You can use your solubility guidelines to determine of these two products here, the lead sulfate or the magnesium nitrate, which one of those two is going to be the insoluble solid. So in this case, the insoluble solid is the solid here, the lead sulfate, and the soluble compound is the magnesium nitrate. All nitrates are soluble. So as a result of this, we aren't really interested in the magnesium nitrate. We want to know whether this lead sulfate is going to produce a precipitate, which also means we're interested in lead ions and we're interested in sulfate ions. So in order to determine this this particular equation and figure out whether this precipitate is forming, I need to know the concentration of lead ions and the concentration of sulfate ions going into the solution. So let's look at two individual solubilities. So lead nitrate, which you'll recall from this side here is soluble, it's aqueous. Lead nitrate, when it dissolves, forms lead ions and 2 nitrate ions. Now we are very interested in the lead ion. Well, we also know a couple of things here. We know the volume of the solution is 100 mils, which is equal to 0.1 liters. And if I take that 0.1 liters and I multiply it by the concentration given in the question at 1 times 10 to the minus 3, the liters cancel out and I produce the number of moles of lead that I actually have in that original solution. I also know that there's a 1-to-1 ratio between the lead nitrate and the lead ion that is formed. So if I have 1 times 10 to the minus 4 moles per liter of lead nitrate, moles of lead nitrate, I also have 1 times 10 to the minus 4 moles of lead ion in solution. Now, this is not going to produce the concentration by itself. The new concentration for the lead ions is the 1 times 10 to the minus 4 moles that we calculated divided by 0.2 liters. That's odd. Where does it say 0.2 liters anywhere in the question? Well, you have to think about what's actually going on in the question. We want to know if in the resulting solution, in the mixture of the two solutions, if a precipitate is going to form. So if you look back at the question, I had 100 mils of this first solution and 100 mils of the second solution being added together. And so I have 200 milliliters or 0.2 liters total in the resulting solution, and so I have to use the resulting solution's volume to determine the concentration of the lead ion. So I actually end up taking 1 times 10 to the minus 4 moles of lead ions and dividing it by 0.2 liters, and I produce 5 times 10 to the minus 4 moles per liter. This is the concentration of lead ions that I have in the resulting solution. I also follow the exact same steps for the magnesium sulfate. Now, I'm not interested in the magnesium ions, but I am interested in the concentration of the sulfate ions because I know that the sulfate is going to be part of the insoluble solid that's formed from this reaction up at the top. So I do the exact same thing. I take my concentration, 2 times 10 to the minus 3, I multiply it by the volume at 0.1, 100 mils, and I produce 2 times 10 to the minus 4 moles per liter. You'll also recall when you look at this, I do again have a 1-to-1 ratio. So I have 2 times 10 to the minus 4 moles per liter, or pardon me, moles of the sulfate ion. Now I take that 2 times 10 to the minus 4 moles and I divide it by again 200 mils or 0.2 liters. And I end up with a concentration of 1 times 10 to the minus 3 moles per liter. So now I have both of the insoluble salts components, the lead and the sulfate ions, with their concentrations in the resulting solution. Now that I have that, I can determine the QSP value. So remember when we talked about Kc and Qc, the reaction quotient, was the exact same equation, but it talked about the concentrations currently before we actually get these things to mix together. So QSP is equal to the concentration of lead times the concentration of the sulfate ion. And we know they are both to the power of 1 because the original stuff, which is the lead sulfate up here, has 1 lead to 1 sulfate. And so our solubility here is 1 lead to 1 sulfate. And all I need to do is take the values that I calculated, so 5 times 10 to the minus 4 moles per liter of lead, 1 times 10 to the minus 3 moles per liter of sulfate, and take the product of them. And I end up with 5 times 10 to the minus 7. And I know that because in the question I was given my KSP, I can compare my KSP to my QSP. And so in this case, my QSP is smaller than my KSP. So 5 times 10 to the minus 7 is smaller than 6.3 times 10 to the minus 7. And so even if I were to mix these two together, I'm not going to produce a precipitate because I'm still able, these numbers here can get larger in order for me to actually produce that precipitate. So I hope that that was clear for you guys. Of course, if we had another situation where this number, let's say it was 6 times 10 to the minus, let's say it was, 7 times 10 to the minus 7, where this is now larger, that means QSP would be larger, a precipitate will form. So that's, that goes without saying. So I hope that was easy for you guys. If you have any questions, send me an email, and we'll go from there. Thanks, guys.